In this section, we will explore how Kafka distributes data using topics and partitions, how keys play a crucial role in ordering, and how log storage and offsets allow for efficient data storage and retrieval. When producers send messages to a Kafka topic, they can include a key with each message. This key is important because Kafka uses it to determine which partition the message will go to. For example, if you are sending payment transactions, you could use the user ID as the key. Kafka will ensure that all transactions from the same user end up in the same partition, preserving the order of events for that user. Without a key, Kafka distributes messages across partitions in a round-robin fashion, which is useful for load balancing, but doesn't guarantee message ordering. Let's walk through this with a payment topic with two partitions and a few user transactions. In this first step, user 1 sends a payment transaction, which we call transaction 1.1. Kafka uses user 1's ID as the key and routes the message to partition 1 of the payment topic. At this point, partition 1 has one message, while partition 2 is empty. Now user 2 sends a payment transaction, which we'll call transaction 2.1. Since user 2 ID is different, Kafka routes transaction 2.1 to partition 2. Now both partitions have data. Next, user 1 sends a second payment transaction, transaction 1.2. Because Kafka uses the user ID as the key, this new transaction is routed to the same partition where transaction 1.1 was stored, which is partition 1. Now user 2 sends a second transaction, transaction 2.2. Like before, this transaction is routed to partition 2, where transaction 2.1 is already stored. User 3 joins in and sends transaction 3.1. Since user 3 has a unique ID, Kafka assigns this transaction to partition 1 for balancing. Now both user 1 and user 3 have their messages in partition 1. Finally, user 3 sends another transaction, transaction 3.2. This message is also sent to partition 1, along with transaction 3.1 from the same user. Now let's explore an important point. All messages from the same user go to the same partition and in the same order that they are sent. This is critical for many use cases like payment transactions, where we want to make sure that the orders of events is preserved. For example, if a user makes two payments, we need to ensure that transaction 1 is processed before transaction 2. By using the user IDs as the key, Kafka ensures that all of a user transactions are stored in the same partition. The order in which these messages arrive at the broker is the order in which they are stored. This means the consumer reading from this partition will receive messages in the exact sequence in which the producer sent them. What are the benefits of this approach? Well, preserving message order is crucial when working with financial transactions, user actions, or any process that depends on sequential data. This setup gives us guaranteed ordering within a partition. Even if there are multiple consumers working in parallel, each consumer will still read the data for a specific user in the correct order because all messages from that user are directed to the same partitions. There are also the benefit of efficient processing. By keeping related messages within a single partition, Kafka can optimize for performance. For instance, it's easier to track offsets and manage consumer progress within one partition. It also simplifies failover mechanism, as the replicas for each partition already contain all the necessary messages for that user. And if a broker goes down, another broker holding a replica can take over seamlessly. In Kafka, partitions are stored as folders on a broker. Each partition folder contains log files, also known as segments, which store the actual data. These segments are created as the data grows. Kafka organizes these segments in sequence, allowing the system to manage them more effectively. All segments can be removed once the data is no longer needed. To visualize this, think of partition 1 from the payment topic being stored on broker A. This partition will have a folder that contains multiple log files like this. Each log file represents a segment, and the numbers indicate where in the data stream the segment begins, based on the offset. Kafka divides the data within partitions into these segments to make it easier to handle and delete all the data when no longer required. Each segment has a maximum size, after which a new segment is created. Kafka uses offsets to track messages. Every message in a partition gets a unique offset. Consumers use these offsets to know where they left off. For instance, if a consumer has processed messages up to offset 105, it can resume from 106 after a failure or restart. Kafka doesn't track what each individual consumer has read. Instead, it organizes consumers into groups and tracks their progress using offset commits. Each consumer group independently keeps track of its own consumption offset, which is the position of the last message it has processed. Kafka stores these offsets in a special internal topic called consumer offset. By committing offset periodically, consumer groups can recover from failure and ensure reliable message delivery. Let's look at how Kafka uses offsets to track data for a payment topic with just one partition. Each message in the partition has a unique offset. Here the consumer A is reading from offset 0, which corresponds to the first message in the topic. As you can see in the offset table below, consumer A is currently reading the payment topic from partition 0 at offset 0. The offset tells us what consumer A is reading, the very first message in the payment topic. This approach ensures that consumer A knows exactly where to resume reading if it needs to restart, maintaining a reliable and consistent view of the data. Now consumer A has processed the first message and advanced to offset 1. This means it's currently reading the second message in the partition. The offset has been updated to reflect this new position. In the table below, we can see that consumer A offset has moved to offset 2. By moving to the next offset, consumer A is able to continue processing messages in sequence. This tracking is essential because it allows consumer A to resume processing right from where it left off if there's ever a failure or restart. To further clarify, Kafka doesn't track individual consumers. Instead, it tracks consumer groups. Let's explore this with the same payment example involving two partitions and two consumers in the same consumer group payment. In Kafka, when consumers belong to the same consumer group, each consumer is assigned specific partition to read from. Offsets are then tracked at the group level, ensuring that if one consumer fails, another within the group can take over processing from the last committed offset. In this example, we have consumer A working on partition 0 and consumer B handling partition 1. Both are part of payment group. Instead of tracking each consumer individually, Kafka tracks payment group as a whole. The offset table shows us exactly which offset is. So if there ever a pause or restart, they will pick up right where they left off. Now consumer A has moved ahead and processed up to offset 1 in partition 0, while consumer B is also at offset 1 in partition 1. This progression means Kafka has a clear, consistent way of tracking what each consumer in the group has processed, and here where Kafka tracking at the consumer group level really shines, by keeping a single committed position for each partition per group. This way, if there's a failover or a need for recovery, the payment group can seamlessly pick up the next offset in each partition, keeping data processing reliable and efficient. Kafka is designed to distribute data across brokers using partitions and replicas. Each partition has one leader and multiple replicas. When a producer sends data, it sends it to the leader of a partition. Kafka replication ensures that the data is safe even if a broker fails. The replicas on other broker will take over as the leader if necessary. So with Kafka, you have both data distribution for performance and fault tolerance for reliability. In this first view, we have two brokers, broker 1 and broker 2, managing two partitions, partition 0 and partition 1 of a topic. Each partition has one leader and one replica. This diagram shows how replication ensures that each partition data is copied across brokers. So if a broker fails, data can still be accessed from replicas on other brokers. In the event broker 1 fails, Zookeeper coordinates the reassignment of the leader role for partition 0 to the replica on broker 2. This enables the fault tolerance in case one broker goes down.